Hello, I'm JW, and this is one video in a series about protective devices as used in electrical installations. In this particular video we'll be looking at RCDs, or Residual Current Devices. This is a typical example as you would have fitted inside a consumer unit. Again, I've got the line and neutral in and line and neutral out the other side, and just a switch there for the manually turning it on and off, and the small test button which you'll find on all of these devices. You can also get these to fit on the end of extension leads, for example. Here's one that wires on permanently. Again, it's got that test button on the front there. You can also get these in a similar style with the plug there and a socket on the back, so you can of course use that with any other appliance you might want to do so. And these devices are only there for one purpose, and it's to disconnect the supply in the event that current goes to places that it shouldn't, such as if someone touched a live wire, or you slashed through the wire of your hedge trimmer and it trailed in the grass. And these are also the devices which are primarily there to protect people rather than the installation itself. So we'll have a look at some of these devices and more importantly how these things actually work and why really you should have these inside your house. Now here's a typical example. This particular one's made by British General, but they're all pretty much the same in design. You've got, in this case, two terminals at the top here for line and neutral, that's the supply in, and at the bottom line and neutral out. And these will always have a connection to both line and neutral because they work by monitoring the current flowing through the device, so obviously through the line and then returning via the neutral. And in normal circumstances, of course, those two currents should be exactly the same. If a fault occurs on the load side of the device and the current can then flow to earth via some other path, the current flowing through here is not going to equal the current coming back, and in those circumstances the device will trip and disconnect the supply. Now all of these have a test button on which basically simulates a imbalance in the current. That's just to make sure that the thing will trip, and if you press the button and it doesn't trip, then of course that would indicate a fault with the device and it would need to be replaced. Now this is a single phase device, it's just got the single line on this side of the neutral here. They are also available in a three-phase variety. This is a YLEX model, and again the similar principle applies, except in this case you've got the three line inputs here and the three line outputs, and again the neutral over that side. So in this case it's three phases coming in, three coming out, and of course the neutral for any current on the return. But again they work in exactly the same way, same test button, and it's just obviously a physically larger device purely to accommodate the extra number of connections. Now it's important to note that these devices do not react to overloads or short circuits. Most of them will have a rating on the front here, in this case 63 amps, but that's just a rating of the internal contacts and switching mechanism. That does not mean it's going to suddenly trip out when you exceed 63 amps. You could put 200 amps through this device, it won't trip or do anything. Again, if you shorted out the supply and several thousand amps flowed through it, again it's not going to disconnect at all. That's purely there as a maximum rating of equipment you can connect downstream of it. In this particular case, the three-phase one, so it's actually only rated to 32 amps maximum. But again, it's not going to trip on 32 amps because it's simply not designed for that. The information of interest on these is the rating here, which in this case is 30 milliamps. And this is the amount of imbalance that needs to occur for the device to trip. So in this case, 30 milliamps or 0.03 amps. And the other information is primarily the breaking capacity of the device, which we'll cover in another video, the voltage of course and the frequency, and obviously the various standards to which the thing is manufactured. Now this device is one which can react to both overloads and has the RCD functionality built in. These are generally referred to as RCBOs, and in this case it has this B32 marking here, which indicates that it is a type B 32 amp circuit breaker. And again, it's got the little test button for the RCD function as well. However, unless you've specifically purchased one of these devices with this functionality built in, then of course your standard RCD is not going to do any of those things. It only applies in this particular case where it's the essentially a circuit breaker and the RCD combined into a single unit. However, we're not going to be looking at those this time. That's just to point out that these things do exist. But again, we'll be looking at those in a separate video. Now, before we look into how this needs to work, let's just have a look at some of the terminology used. This is BS 7671, which contains all of the relevant definitions, and here we've got residual current device, or RCD, And as it says here, mechanical switching device or association of device is intended to cause the opening of the contacts when the residual current attains a given value under specified conditions. And that's the 30 milliamps we saw on the device previously, though of course it can be various other values. The RCBO here is the one with the built-in circuit breaker, so again, as it states here, it will work on both the residual current and when there's an overload or a short circuit. And RCCB, or residual current operated circuit breaker without integral overcurrent protection, is basically the same as the RCD, it's just a different name for the same device. And the residual operating current is the residual current which causes the RCD to operate under specified conditions. Now, residual current is a fairly odd term, but nevertheless we'll see what that one actually is defined as. That's on the previous page. Now, residual current is defined here as the algebraic sum of the currents in the live conductors of a circuit at a point in the electrical installation. Now, in this case, live conductors refers to both the line and neutral conductors, because those are both live conductors. Notice the difference between live and line. Unfortunately, a lot of people call the line conductor live, but that's another story. And algebraic sum, of course, is simply adding the two currents together. Now, in this case of this particular RCD here, we've got the line which comes in here and comes out here, and that will go off to a load or some other device over there. And of course, to complete the circuit, it will come back via the neutral in here, and of course out of here, and that's back to the supply. So if, for an example, we had, say, 1 amp coming along into the circuit, of course 1 amp is going to flow through the entire circuit, because obviously that's how circuits operate. But the algebraic sum of those is 1 amp coming in this direction, so we'll call that, say, plus 1 amp. And of course, coming out again, we've got the same current, but it's in the opposite direction, so we can call that minus 1 amp. So of course, plus 1 minus 1 equals 0. And under normal circumstances, it's always going to be 0, because whatever current goes in here is going to go through the load and of course return back to the supply. So whether it's 1 amp or 100 amps or any number of amps, the algebraic sum is always going to be 0, and that's purely due to the fact that it's going to be the same in both directions, and of course one direction cancels out the other. However, when there's some kind of fault or other issue occurring on the load side here, some of that current is going to leak away to earth, and the return current is not going to be exactly the same as the current coming in. And this is the residual current, or what's basically left over after you've added the two together. And in this case it's a 30 milliamp device, so at 0.03 amps would trip this device, and again you can get these in various other ratings. The fact that this is an AC device doesn't change anything. It simply means that in one part of the cycle the current would be flowing through here and coming back this way, and of course on the other half of the cycle it would flow through here and of course come back the other way, but in all cases the sum of that is going to be 0 unless there's some kind of fault occurring on the load side. Those definitions were from BS 7671 2008, which is the current edition at the time this video is being made, which is August 2014. Obviously this may have been updated if you're watching this many years in the future. Now the mains power comes into your house will be supplied via a transformer. Generally that'll be outside in the street somewhere, and that's just there to change the high voltage, generally sort of 11 kilovolts or something, to a more sensible voltage. In the case of the UK that's generally going to be around 230 volts. And we'll call that the line and the neutral here. Now in this condition, of course, this is just effectively an isolating transformer. You've got 230 volts between the two, but of course that's all. But in of course the real world, there's also a connection here, which goes down to the ground, or the earth as it were. I'll just draw that in like that. And of course this means that you've got the neutral here and the earth effectively connected together, usually at the transformer and in some cases other places, so the voltage between the two is effectively going to be 0. They're both going to be at the same potential throughout the rest of the system, and of course the 230 volts can then be referenced either to the neutral or to the earth or ground as well. And this is why if you happen to be standing on the ground and you touch a wire at 230 volts, you will probably kill yourself, because of course the voltage will then flow through and return back to the point at the transformer. Now the wires obviously come into your house, and if we're going to put an RCD in here, we can have, say, the line coming in here, and then we'll say have the neutral coming in alongside. And all that's in an RCD is, of course, first of all, you're going to have a switch of some kind. So we'll just draw a switch in there. Generally, these are double pole switches, although there's no particular reason why it wouldn't be a single pole also, but we'll draw in a double pole with some kind of actuating mechanism. Could be a solenoid or some other kind of actuating device just to trip the switch when necessary. And the actual sensing part is incredibly simple. In older ones it was just a magnetic core, and the two wires would come in and basically wind around the core, and of course the neutral would do likewise. And then this will go off to whatever load or equipment you have attached to the equipment. So in normal circumstances the current would flow through here, through the coil on there, through to the load, and then of course return via the same path and back to the supply. So one of these coils will create a magnetic field within the magnetic or iron core, and when the current comes back it will contain another magnetic field here, and of course these are arranged so that one will cancel out the other. So in normal circumstances the actual net result in here will be 0. Of course, when somebody touches the live wire, or there's some fault over here, so we put a person here standing on the ground. If somehow the live wire came into contact with the individual, some of the current, of course, now will flow via the path here back through the earth to the transformer, and obviously some will go via the neutral as it was intended. So you'll have an imbalance here of the two currents, so generally the current going out would be greater than the current returning, and this will cause obviously a magnetic field to be generated within the core. Now to detect this you need a third winding, which we can put in here, and that will connect into the tripping device or relay or solenoid or whatever else it is you have there. And if that reaches a certain level, then of course that will trip out the device, disconnecting the supply. Now, at one point there were actual RCDs made in this fashion, but there's a significant problem with this because it means that the wires going into the coil here, and obviously on the return, have to be sized to carry the full load of whatever is actually going through here at all the time. And of course, if it's a fairly moderate size RCD, say sort of 40 or 50 amps or something, these wires in the coil have got to carry 40 or 50 amps pretty much indefinitely. This makes the wires quite large, and therefore makes the actual device itself very large, and of course therefore rather expensive. So most modern RCDs are not actually made in that fashion, so we'll just erase that away, and we'll just draw that in again with the more likely scenario. The usual way now is to still have a magnetic core made out of sort of ferrite or some other material, but instead of actually winding them around, the two wires actually just go through the centre, and of course the line will go through the centre just the same, and again that goes off to your load or whatever. The sensing coil is basically still the same, and that would just go around the core like that. And in this scenario, of course, the wires going through can be any size you like. They're just going literally straight through the centre, and again the sensor coil just detects the current imbalance and will trip the device as necessary. This is generally how the modern RCDs are actually created, and the sensing device here could be, in theory, just a solenoid with a appropriately arranged massive coil here and a coil here. But again, in modern ones, it's generally some kind of electronics in here, which contains an amplifier and various other things to obviously trip it at the predefined leakage current. This can easily be extended to a three-phase device, or with three lines coming in. All that happens is you've then got the two additional conductors there coming from the supply. There'll be an additional two switch contacts, and then all that happens is that the additional ones simply go through the centre of the magnetic core along with the rest of them. So it's simply monitoring the current across all four conductors, and again it works in exactly the same way. If there's any kind of imbalance, that is detected here and of course will trip the device. Now, one vitally important point about RCDs is that they only work if the system itself is referenced to ground, and of course in normal mains supply that's exactly what it will be, because there's always a connection from the neutral to the actual ground itself. That's certainly going to be the case at the transformer, and in most cases there'll be multiple connections elsewhere within the system. But there can be instances where the system is not referenced to ground, so effectively this section here does not exist. And this sort of thing might occur if you were using a portable generator, for example, which of course is a self-contained device, and although it generates the 230 volts as supply, that may or may not be referenced to ground. So of course if it wasn't referenced to ground, somebody, say touching the wire here, isn't actually going to trip any kind of RCD, simply for the fact that there's no return path for the current. So voltage supply here, the person's touching it, so they would be at the same potential as the terminal here on the generator, but nothing will actually happen because of course there's no return path for the current back here. This also means that the person wouldn't actually get an electric shock in these circumstances, simply because again there's no return path for the current. And a similar thing can also be done just by using an isolating transformer, which may be used for various testing procedures. And a lot of small generators generally don't have the conductors referenced to earth for this reason. They're generally intended to supply, say, a single piece of equipment, and in that circumstance it's actually safer just to have a floating or isolated supply and not have it referenced to ground, which obviously avoids any kind of problems here. However, if you've got a larger generator and it's therefore supplying quite a number of different pieces of equipment, this situation is actually fairly dangerous, because any kind of fault on one of the pieces of equipment, sort of on the load side over here, if one of those somehow became connected to ground in some fashion, of course initially you're not going to notice, but as soon as someone then touches one of the conductors elsewhere, they're fairly likely to get a shock, because the path will then go via the person through the other fault that's occurred and of course return back to there. So larger generators would generally have one of the supply lines connected to earth, as in the connection here, or in some cases it might be a centre tapped arrangement, so from the middle of the transformer like that. And obviously that would not exist in that particular case. In that particular situation you would generally have say 115 on each relative to earth, and again the RCD would then trip properly. So if you do have a generator which has this kind of setup, it's absolutely vital that the connection there is actually put into the ground using with a earth rod or earth stake of some kind. Otherwise the RCD that's usually included in these devices won't actually do anything in the event of a fault, and if you're powering several pieces of equipment, that could easily lead to a very dangerous situation. Now, as well as RCDs like this, which will trip the supply when the current imbalance reaches a predefined level, there are some other devices which are essentially the same inside, but they don't contain a disconnection or a switch at all. Essentially the wires are just coming straight through the coil, and in this case the sense coil will be connected to some kind of monitoring device, obviously generally with electronics and such like in it, and typically that would have various sort of indicators or warning lamps upon it, and possibly some sort of display which would display the actual leakage current instead. And these devices are generally called RCMs, or residual current monitors, and they're typically used in large installations where there's inevitably going to be some kind of current leaking away to earth, simply due to the fact of the equipment that's installed. And this might be, for example, a data center full of computer equipment, or a large sort of office or something like that. And these devices are typically installed to monitor that current and either display it on a numeric display, or some have sort of indicators to indicate various levels of current there. And typically they'll have something like audible alarms, or might connect into a building management system. The idea being that if some fault occurs where the current then increases beyond a predefined limit, rather than disconnecting the whole building and causing massive inconvenience, it will just sound an alarm, and therefore the problem can therefore be investigated and repaired when it's more convenient. Obviously you wouldn't want an entire data center full of thousands of computers just being suddenly turned off because some minor piffling fault occurred somewhere in the building. So look there at RCDs, or residual current devices. They do go under other names in other countries, such as GFCI, I think, in the United States. But either way, the principles are the same. It just monitors the current flowing in and out of a particular load or installation, and will disconnect the supply in the event of an imbalance occurring more than a predefined value. And typically those installed to protect people and other equipment would generally be in the 30 milliamps range. And you can get ones lower than that, but they're not particularly commonly used, because there can be issues then with equipment and things causing trips anyhow, even when there's no fault. And larger values do also exist. 100 milliamp ones, for example, would be used in circumstances where the earth loop impedance is too high, typically if you've only got an earth rod at your earthing facility. And again, much higher ones are used for sort of fire protection and in more specialised applications. And if you have one of these in your house, you need to test them at regular intervals, simply by pressing the test button, and the device, of course, should switch off once you've pressed that. If it doesn't, then of course the device needs to be replaced. And it's important that these things are checked regularly, because the mechanisms, of course, can stick closed, and being mostly electronic now, they can obviously develop faults internally. And these things really are lifesavers, because exactly the point of them is to disconnect the supply if you accidentally come in contact with a live wire, something which fuses and circuit breakers will not protect you against, as the current flowing there would be far too small to trip even the smallest sort of 6 amp circuit breaker, and it would essentially just continue to pass the current through your body until some other method of disconnection occurred. So until next time, thanks for watching.